Now let's consider example 3, and it's actually the same as example 1 and 2, but this time we're going to use Lagrange interpolating polynomial in order to estimate the linear and quadratic interpolating curves. If you recall, the Lagrange interpolating polynomial is given by this equation, f sub n of x, where n is the order of the polynomial. So if n is equal to 1, then we have a linear version, and n equals 2, we have the second order version, or the quadratic polynomial. Key feature here is this expression. So we have the Lagrange expression written as this, where it's the product of these terms. So the idea is to be able to multiply these products, keeping in mind that j must not be equal to I, where I is the ith term in the polynomial f sub n of x. So this is the MATLAB code. As you can see, from here up to pretty much here, the solution is the same as that in the MATLAB code for example number 2. Of course, we all know that when n equals 1, we're considering the linear term. When n equals 2, we're considering the quadratic term, and so on and so forth. So in this case, since we only have 3 points, then we cannot go more than n equals 2. So our solution, the maximum order in order to solve the solution, is quadratic, or 2. So in this case, I use the function f sub n of x. I have these in comments. This is the brute force typing in method of the Lagrange interpolating polynomial as shown in the previous slide, just to check whether this function works for second order. And this is the function. So you can see here the function f. The f is the return value. F2 is the name of the function, and x, y, n, and w are the input variables. In this case, the first input variable is double x. Second input variable is fx. Third input variable is n, which is the order, and x is the abscissa in the graph. Xx and fx are your given values. So we have the given values inside this function as x and y. This is the order, and this is the abscissa of the graph. So this initializes the return parameter f. Okay, so this is 0. We set all elements of the matrix or the variable 0, and this variable has a 1 row, and this matrix has a number of elements equal to the length of w. Okay, so we have 4 loops here, and the first for loop will give us the sum, okay, of f sub n. The second for loop actually solves for the Lagrange product terms, and the first for loop solves for the polynomial. If we go back here, this is our polynomial, and this is our Lagrange terms. So the Lagrange terms are basically a product, and you run this code by using a for loop for this product, and this is what happens. So initially we set the variable product to a matrix of 1 row and number of columns which is equal to the length of w, and all the elements of that matrix are just ones. So this is just a matrix where all the elements are unit values. So next we solve for this one, and I call this as temp. So if I is not equal to j, then temp is equal to this expression, w minus xj and divided by xi minus xj. But if I is equal to j, we simply multiply this by a matrix which is equal to 1, and that's what I have here. So this is a matrix with a 1 row and the number of column elements equal to the length of w, and the element values are just ones. So essentially I'm just multiplying this by 1 if I is equal to j. And for each iteration in the jth index, whatever the value of temp here, whether it's this one or this one, it's just multiplied here. So Okay, so let's consider this example. Let's consider a quadratic polynomial. So that means that n is equal to 2, which means that this for loop will run from I equals 1 to 3. So there will be 3 elements in this polynomial. So let's start with I equals 1. So if I equals 1, then product equals 1 length w. And then for j equals 1 to 3, okay, so let's begin with I equals 1 and j equals 1. This means that in this case temp is equal to this just once. So since initially this is just once and this is once, then that means this is once for j equals 1. For the next iteration for j equals 2, I is no longer equal to j, so temp will be computed as this, w minus x2 minus x1 minus x2. And since this is just 1 for j equals 2, then this is multiplied by w minus x2 divided by x1 minus x2. So the new prod value will be w minus x2 minus all over x1 minus x2. Now for j equals 3, since I is still not equal to j, then this temp will be equal to w minus x3 divided by x1 minus x3. And since this is at the moment w minus x2 over x1 minus x2, and this is w minus x3 over x1 minus x3, then this new product will become w minus x2 over x1 minus x2 times w minus x3 over x1 minus x3. And it terminates up to 3, so that means that this the final value of this product will be here. Now yi, so yi in this case, so it's y is the first element of fx, okay, which is 0 in this case. So since this is initially 0 and this is 0 for yi, and this f is 0 for I equals I. Then you do the same for I equals 2. Now for I equals 2, only when j equals I does the temp take on this value. Otherwise, temp will take on this value. This time, yi is no longer equal to 0, so the product that will be computed for j equals 2 iteration in the second for loop will be multiplied to the value y of 2. And that will be added to 0 here, and this will have a new value when it goes to I equals 3. So when I equals 3, this initializes the product, and then we'll have a new product at the end of this for loop. Okay, and then that new product will be multiplied by y3, and this result will be added to the previous value of f so that it will have a new value of f. So this f now will have already 2 terms. This will be returned to the main script, which is here. So whatever f we have computed there will be placed in this variable f. Okay, so we can plot f here, and then we can also solve for f2, even if you just used a single data point instead of a set of data points. Okay, so that's pretty much it.